Let's look at some examples and hints. Iron plus bromine produces iron 3 bromide. Before we start balancing the equation, remember that the subscripts cannot be changed. However, this reaction is not balanced. There are 2 bromine atoms on the reactant side and 3 bromine atoms on the product side. Balance the bromines by finding a common multiple. Put a 3 in front of the Br2 and a 2 in front of the FeBr3. This gives us 6 bromine atoms on each side of the equation. The equation is still not balanced, however, because now we have 2 iron atoms on the product side and only 1 on the reactant side. We can correct this by putting a 2 in front of the iron on the reactant side. And now we have a balanced equation. We can prove this to ourselves by counting the number of atoms. We have 2 irons on this side. We have 2 irons on the other side. And we have 6 bromines on the reactant side. And we have 6 bromines on the product side. Another equation. Tin 4 nitrite plus potassium phosphate produces potassium nitrite plus tin 4 phosphate. Oxygen is present in all 4 of these chemical compounds. So ignore the oxygen to begin with and balance the other atoms first. And by the time you finish, the oxygen atoms may already be balanced. 1 tin atom appears on the left side of the reaction and 3 appear on the right side. We can try balancing the tins first by putting a 3 in front of tin 4 nitrite. We have 3 tin atoms on this side of the equation. On the right side of the equation, we have 3 tin atoms already. So the tins are balanced in this case. Now we consider the nitrates. On the left-hand side, there's the nitrate, and there are 4 of them in each tin 4 nitrate molecule, but we have 3 of those molecules right now, so we have actually a total of 12 nitrates on the left-hand side. So to balance the nitrates on the right side, we place a 12 in front of potassium nitrite, and the result is that we have the same number of nitrites on each side. We now have 12 of them here as well. We also now have 12 potassiums on the product side of the reaction, so we need to balance the potassiums on the reactant side where there are only 3. To make this number of potassiums equal 12, we put a 4 in front of this whole compound. When you multiply 4 times 3, that gives us 12 potassiums. It also gives us 4 phosphate molecules, and if we look over on the product side, we see that there are already 4 phosphate molecules on that side. So our equation is now balanced. A final check of individual atoms. In particular, let's look at oxygen atoms because we were sort of leaving them till last. Let's see what we've actually got here. We've got 2 times 4, that's 8 oxygen atoms, times 3 is 24. And over here we have 4 times 4, that's 16 oxygen atoms. That gives us a total of 40 oxygen atoms on the reactant side. And on the product side, let's see what we've got. We've got 2 oxygen atoms here times 12, that's 24. And we have 4 times 4 oxygen atoms here, that's 16. Add those together and we have 40. So in addition to all the other atoms being balanced, the oxygens also are balanced, which gives us a completely balanced equation. 3 tin 4 nitrite plus 4 potassium phosphate produces 12 potassium nitrite and 1 tin 4 phosphate. One more reaction. Ethane plus oxygen produces carbon dioxide and water. Ethane is a byproduct of petroleum refining, and like the other reaction, this is a combustion reaction where something burns in the presence of oxygen to produce carbon dioxide and water. First, let's balance the carbons. We have 2 carbons on the left side and only 1 on the right side. If we put a coefficient in front of the carbon dioxide molecule, that gives us 2 carbons. Because oxygen appears in so many places in this chemical equation, let's ignore it again till last and hope for the best. So let's take a look at the hydrogens. There are 6 hydrogens on the left side and 2 hydrogens on the right side. We need to balance them. So if we put a 3 in front of the water on the right side, that gives us 6 hydrogens, and that's equal to the 6 hydrogens on the left side. Okay, so if we take a look at the oxygens now, they're not balanced, and hoping for the best didn't work out in this case, so we need to do a bit of a fancier maneuver. We have 2 oxygens on the left-hand side, and we have 4 oxygens plus the other 3 oxygens from over here for a total of 7 oxygens on the right side. This is not going to work. So on the left side we have 2 oxygens, and on the right side we have 7 oxygens, and we need to balance this out. If we had 3.5 oxygen molecules over here, that would actually give us the right number of oxygens, because 3.5 O2 molecules would look like this. There's 1, 2, 3.5. That's actually 7 oxygen atoms, and it's just what we need. But the idea of having a fraction on this side isn't very appealing. So what we do is we double everything, or we multiply through so that we have an even, so we have no fractions. So if we do that, we come up with this 2C2H6. 2 times 3.5 is 7 O2s. Produces 2 times 2, which is 4 CO2s, and 2 times 3, which is 6 H2O molecules. Now we have to have a balanced equation, and we don't have any of those messy fractions to have to deal with. Okay, so I guess the moral of that story is that you might have to get creative with your math to balance the equation. Remember though, there are 2 major rules. You cannot change the subscripts, and you can only manipulate the coefficients in front of each of these molecules or elements. So good luck, and I hope you have some happy balancing as you work on the problems.